All right, hello everybody. How's it going? Everybody's tired by now, I guess. That's the disadvantage of this class. Some people are asking about the midterm, so as I said on EAS2 just recently, we'll do it on October 29 on Wednesday. Before we will do the practice problems and so on. I have one more homework or project coming up for you. I guess I will assign it tomorrow as usual. And then we will start to do a little bit of these practice problems for the midterm. If you want to start doing something already, then try going over all these terms like orthogonal and basis and try to remember what all they are. The best way to remember is by solving problems from the textbook or from the midterm practice problems that I posted before. Okay? Okay, so today I would like to finish the 4 fundamental subspaces, which is a pretty cool thing because it gives you the complete picture of what a rectangular matrix does. It's like one of the nice things that it doesn't require a lot of involved mathematics, but gives you lots of knowledge, if you want to put it that way. It essentially, if you look at the rectangular matrix as a mapping from Rn to Rm, it will tell you what exactly this mapping essentially is doing. It's like a constructive approach. Like this. So before we get there, we need to talk a little bit more about subspaces. We sort of started the last time, but there is a few things that I need to elaborate on. You know, let's start very briefly. As I said, you need to remember the definitions. So we will start with recapping the definition of a subspace. So what was a subspace S, meaning of a vector space V over the reals, right? If we always assume we are over the reals here. So the subspace S was a subset, right? Subset of V, but not just any subset. What were the properties? We will be talking a lot about subspaces today, so let's just quickly review what is a subspace. So it must be a subset, right? But what? Not every subset would be a subspace, right? Yep. Contain 0. That's correct. Yeah. What else? Exactly. So once I have so first is closure over addition. So closure means that if I take any 2 vectors from the subspace, then it implies that x plus y is also going to be in the subspace, where this plus refers to the vector addition from the vector space V, right? Property number 2 is that for every x from S, every vector x in the subspace, and from every scalar, the scalar multiple of x is also going to be in the subspace. So closure with respect to vector addition and scalar multiplication, right? Those are the two key things of a vector space. If the subspace is self-contained, closed, in the sense that these 2 operations don't run away from S to some larger space, larger subspace possibly, then this is a subspace. So why do I have to put there the 0 specifically? It is absolutely true, you're absolutely right, that 0 must be in every subspace, right? Why don't I have to like write here number 3 that 0 is there? Yep. It immediately follows from point 3, right? Because I can put 0 for alpha, so it's already contained there. Perfect. So you remember this. That's awesome. Now let me give you an idea. Why do we bother about what is like philosophically? Why is it good to reason about subspaces? If instead I could be reasoning about linear combinations of some vectors, right? We had the concept of a basis. We know that every vector space has a basis. Let's not worry right now about the infinite dimension vector spaces. Let's just consider the nice and tamed of finite dimension vector spaces. So that's not my point. My point is, yeah, why do we care about this concept of a subspace if instead I could just say, well, let's pick some basis and let's do a linear combination of the basis vectors. And that basically characterizes all the vectors in the subspace, right? So I guess this is more philosophical, even though it has real mathematical implications. The reason why it's nice to talk about the subspace, let's imagine, for example, let's imagine a 2D subspace in 3D, okay? And let's say I'll just draw it as a plane, but imagine it's like just an arbitrary plane in the 3D space somewhere, okay? And if I wanted to describe it using a basis, I need to pick a basis, right? You would probably pick this basis, but nothing prevents you from picking this basis, right? Or you could even equivalently pick a basis like this, Why not? It's a perfectly valid basis, right? So my point here is that there is many bases in every subspace, so that's not unique. But if you think about it just in terms of the subspace, the plane is the plane period, right? The subspace itself is unique. And that's why it sort of makes sense to think about the matrices in terms of subspaces, because it essentially lets you not worry about the specific basis of the subspace, okay? You can totally do everything in bases, but then you sort of have to worry about, okay, what if I pick a different basis? Will these properties I'm talking about still hold? Well, if you do it in terms of subspaces, you don't have to worry about it, because you can have there a basis or not. Do you see sort of what I'm saying? Good. So keep this in mind. I think it will come up later. So we talk in terms of so let's go back to the main point today. So we have a matrix which is rectangular, m by n, right? That's what we started studying before. And we introduced a few important subspaces of the matrix. So that was the column span. So can someone remind me the definition of the column span? That's I guess the easiest one to think about. You can even say it in words and then translate it into math symbols. Anybody remembers the column span of a matrix? The C of a matrix? It's simply a linear combination of all the columns, right? So I can write it like this. X is from Rn. And a linear combination of the columns. I hope everybody does see that the AX really does a linear combination of the columns of matrix A. Again, so you need to have the center of your brain for matrix vector multiplication developed. I'm just, I hope this is something boring for you. I hope this is not something new. So the other space we had there was the null space. So what was the null space of the matrix? The same matrix, different subspace, but still a subspace. By the way, you should also be able to, like, if I ask you why this is a subspace, you should be able to argue why. It's simple, so I'm not gonna waste time on that because we need to move on. So what about the null space? Anybody remembers that? That's again one of the things. Yeah. So if you don't remember these things, then it might make sense to invest some time into going through the lectures or the definitions. Let me just do it in the interest of time. So that would be all a set of vectors x, also from Rn, such that Ax equals 0, right? The set of all vectors which the matrix A sends to 0. Okay. And then did we talk about the row space? I think we did a little bit, right? So the row space is essentially equivalent to the column space of AT. So if I talk about the row space of A, it's equivalent to the column space of the transpose of A, which is really nothing, but I can just write it like this, right? AT, let me put there y so we don't confuse, because y is now an m-dimensional vector. Equivalently, I could also write this, I think I discussed this the last time, like this YTA, right? And from YTA, y is a row vector, so you can see this is really doing a linear combination of the rows of A, right? So this is a row span, or row space. Space or span doesn't matter, I just use it as synonyms. Okay? And what is the fourth one? I think I mentioned the fourth one too, right? There's 4 fundamental subspaces. So what is the fourth one? The last one. So it would be number 1, number 2, number 3. What is number 4? It's been a really long fall break. So number 4 is the left null space, which is equivalent to the null space of A transpose. Like symmetry sort of dictates this, right? You can see the beautiful symmetry due to similar to what we have seen in groups. And that's the set of vectors y such that ATY gives me 0. Okay? Y in this case are m-dimensional vectors. So I guess if I was to be like really pedantic, I should say this is a 0 transpose because it's a row vector of all zeros. Okay? So that basically this I can transpose both sides of the equation, right? So this is YTA equals 0. I guess it could be even more pedantic by putting it like a vector. I just want to say that this is a column of all zeros, right? So the vectors in the left null space are all such vectors y, such that when multiplied with A from the left, they give me all zeros. Okay, and that sort of completes the picture. Do you sort of see the symmetry there? There is even better symmetry, which is basically the point of the 4 fundamental subspaces. I think Gilbert Strain calls it the fundamental theorem of linear algebra, and I think that makes a lot of sense. So we will get there. Okay. Everybody happy about these definitions? We're gonna talk a little bit more about that. I think I already discussed how to get the basis of the column span. Let's talk a little bit about the row span now. In particular, how, if you need to get a basis, how can you do that? So you can do it, well, our old friend is reduced row echelon form, so we convert it to reduced row echelon form. Again, my A matrix is m by n, right? So the transformation matrix, the product of elementary row transformation, is an invertible m by n matrix. And again, I hope you remember what GLM was. That's what I just said, invertible m by n matrix. And let's think about it. So how could we get from this decomposition the basis for the row span? So let's wait a second. Well, let's finish this. Then I need to go back to orthogonal complement. Maybe let's write this graphically. I think that's a little more intuitive. So let's assume that A is like this type of matrix, for example. So then E, so this is A. And E is a square, right? M by M, invertible. So it's a good matrix. And R is the reduced row echelon form. So it's something like this, right? You know what, let's do it just like this, and then like this. It's not so big. So it's 1, there is something here, 0, 1, 0, 0, 1, something here, something here, something here, something here, something here, something here. Then would be, let's put another row here, column like this. And then there is some numbers which I don't really know what they are. They can be zeros, they can be non-zeros, they can be whatever. So this is the R matrix and Hicksund zeros, okay? And this number of the rows, that's the rank, right? That's the lowercase r, that's the rank of the matrix. So now can you tell me what is the basis of the row span of A? Just by looking at this picture. I sort of like best if you can just like look at it and get it from the picture. Which in this case you can. Because what is the row span? It's the subspace formed by all linear combinations of the rows of A, right? So here A has some rows. If I take arbitrarily linear combination of the rows, I get a vector in the subspace, and I can get all vectors in the subspace by doing this, right? So let's see. Oh, that's exactly what's written here. So notice that every row is linear combination of the rows in R. That's essentially what the matrix E tells us. That's what the matrix multiplication E times R tells us, right? If I take an arbitrary row in A, I can take the same row in E, and I just do a linear combination of the rows of R with it. Do you see it? Again, I'm just referring to your matrix multiplication intuition. So let's like the second one, A2, here would be some E2, right? So what the A2 is, it's just E2 times this, right? So that means linear combination of the rows of R, right? And every row of A is just a linear combination of the rows of R. Well, that means that the rows of R exactly span the entire null space, right? And if I take away these guys, which are zeros, so they don't really matter. So if I keep only the first R ones, well, they will already be linearly independent, right? And if they span the subspace and they are linearly independent, then they are what? They are bases, right? That's how basis was defined. So the basis we immediately read of here. So the first rows of R are immediately the basis of the row space of A. So why are they linearly independent? Can you quickly give me an argument? These first R rows in R, and why I cannot put the 0 ones there. That would destroy my linear independence. Well, again, the key is to remember how linear independence was defined, right? And linear independence was defined that it means that if I take the first vector, I'll just do it quickly because these are simple things. If I multiply this by alpha, this by beta, this by gamma, this by delta, and I have such a combination that gives me 0 vector, then this must imply that all of them must be 0. Alpha must be 0, beta must be 0, gamma must be 0, delta must be 0. Yep? Exactly, that's exactly right, yes, because the pivot columns, they have zeros. I said this is zeros everywhere, right? I can just write them there explicitly. This directly tells me that alpha is 0, right? This tells me that beta is 0. This tells me that gamma is 0. This tells me delta is 0. So that's immediately there. It's obviously linearly independent, right? Basically, the other way, you can see there like the identity submatrix in there, right? Identity certainly is, the standard basis vectors certainly are linearly independent. So, and end of discussion. Now, what if I by mistake put there these vectors which are all 0? Would it still be linearly independent? If I said let's include, so I included these 4, the rank guys, right? And I have other vectors which are all zeros. Can I put them in the basis? I cannot, right? Because if I put them there is, and I would have some other, I don't know, epsilon thing, there would be nothing saying that epsilon must be 0. Epsilon could be arbitrary, so it would not be linearly independent, right? Once you put the 0 to a set of vectors, it can be linearly independent. Okay. So yeah, so here is just summarized what I just said. So they are linearly independent. That's why. And we have R linearly independent pivot rows. They are also called pivot rows, and they span the row space. And so they span the row space of A, aka the column space of AT. They are linearly independent, and therefore they are basis for the subspace, right? For the, maybe I should say, basis for the subspace CAT. And if you put it together with what we said before on Wednesday last week, then clearly the dimension of this subspace, the row space of the matrix, is R, right? The same thing was true for the column span. So if you put it all together, then it doesn't matter if you are looking at the dimension of the row span or column span. They both have the same dimension, and that happens to be R. So it's beautifully symmetric. It's maybe not so obvious, right? Because we are looking, it's not immediately obvious because we are looking at rectangular matrices, right? So that's something that I guess you would probably not be immediately obvious to you, right? If I give you an arbitrary rectangular matrix, so then it doesn't matter if you are looking at linear combinations of the columns or rows, because the dimension of both subspaces is the same. Okay? So here is a concept of orthogonal complement, which I will need in the 4 fundamental subspaces. This theorem. So we talked before about orthogonal subspaces. Orthogonal complement is a little bit stronger requirement. Let's just recap real quick. So I think this is needed. What were orthogonal subspaces? If I have subspace S1, subspace S2, and they are orthogonal, what does it mean? Something really simple, right? So. Yep. If I pick any vector from the first one, and if any vector from the second one, then there the product is 0. That's exactly correct. Yes. So orthogonal complement is a little bit stronger notion, because if I take, so the idea is if I take a vector subspace in Rn and I define its orthogonal complement. By the way, this is the notation. not to be confused with the transposition, because it's like an operator that operates on a subspace and returns me the orthogonal subspace to it. And what the orthogonal subspace or orthogonal complement is, these are all vectors which are orthogonal to all vectors from X. Okay, all vectors, like I guess I could write here I from R to N, right, to be even more pedantic, if you will. They are both from the same vector space V. X is a subspace of V. It's very easy to prove that also the orthogonal complement of X is a vector subspace, right? Again, very, very trivial. All I need to prove is the closure properties. That's what I started with here. So that's very simple. Now, an interesting thing is, let me give you, I guess, before we go there, let me give you an example. So let's start with a trivial example. So if I have this subspace, if I'm in R2, and I have this subspace S, which coincides with the x-axis, what is the orthogonal complement, do you think? The y-axis, correct. So this would be S orthogonal complement. What if I'm still in 2D and I take this one? What's the orthogonal complement? Nothing, no rocket science, right? It's just, you can just build it. Exactly, the perpendicular line. So if this is, let's call it X this time, because I call it X at the first place. This is the perpendicular, the orthogonal complement of X, right? It gets a little more interesting in 3D. If I have a, let me not draw the 3D thing, but let's just imagine it. If I have a line in 3D, what is the orthogonal complement to it? Line passing through the origin, of course. Yep. Plane perpendicular to it, right? Also passing through the origin, of course. And the other way around, if I have a plane passing through the origin in 3D, what's the orthogonal complement to that? Something symmetry, right? It's the line that gives me back the line. Actually, it appears that it's always true that if I take orthogonal complement and I take another orthogonal complement, I get back to the original subspace. So here is why the orthogonal complement is like a little bit stronger requirement than just orthogonal, because in 3D I can have two orthogonal subspaces which are just lines, right? I can easily have two orthogonal lines in 3D, but they would not be one would not be orthogonal complement of the other, okay? And that's because if I'm taking the orthogonal complement, that basically if this one subspace has dimension R, then the other subspace must have dimension n minus R. Basically, it picks up the entire rest of the space. So any vector in the original vector space can be written as a combination of vectors from X and X orthogonal complement. Maybe let me illustrate this visually. I like this sort of drawing. So let's do a 3D example. And let's say that one of my subspaces is a plane, like it's an infinite plane, but because I don't have infinite space, I'll just draw a finite one, right? By the way, all these drawings, they need to be interpreted with a pinch of salt always, right? Sometimes they actually do more harm than good in some cases. Like last time somebody was asking me when we were talking about the infinite dimension vector spaces, where are the arrows, right? So these visual, like intuitive aids or drawings, they only stretch that far, right? All that ultimately matters is the hard mathematics, right? These defining properties. And all these things are just intuition, which is very useful for us because sometimes it works, but just don't rely on it 100%, right? Not every vector is reasonable to understand as some sort of arrow, okay? Nevertheless, here the intuition is very instrumental. So if this is my subspace S, and I'm in 3D, then the orthogonal complement to it is a line, right? So if let's say my origin is here, this is my 0. So the orthogonal complement would be like a line like this. This would be S orthogonal complement, right? And what I'm saying here is if I pick an arbitrary vector, so here actually the arrows work very nicely. So if I pick a vector V, that's from the original 3D subspace, right? So let me write this. Then I can write it as a sum of two vectors where one would be in the subspace, so it would be, let's call it V1, and the other one would be in the orthogonal complement. So V1 would be in S, and V2 would be in the orthogonal complement of S. And if I sum them together, V1 plus V2, I get the V. Okay? So that's the idea. We will talk about this more when we will talk about least squares and Gram-Schmidt, so we will revisit this idea, but I think the basic idea is fairly clear, right? You can split it into two components. One is in one subspace, the other one is in another subspace. Because the other way you could also put it is that the span of S and S orthogonal complement is the entire vector space V, where V is the original vector space we started with. By the way, what are some trivial examples? I guess I should have also started with trivial examples. First, trivial examples of orthogonal complements would be this, right? We have the two trivial subspaces, which are always correct examples of subspaces, even though they are really dumb. But it's good to think about, so what is the, if I take just 0, what's the orthogonal complement of that? I take just the origin, that's it. The orthogonal complement of that would be the entire space, right? And the other way around, the orthogonal complement of V would be just the origin. This would be like a 0-dimensional subspace, would be like n-dimensional subspace. So even this equation still works, right? If that's 0 and minus 0 is n, so that everything is cool. Okay. So a few more comments about the matrix subspaces. So remember, let's talk for a little bit about the null space to understand it a little bit better. So I said before that the null space is defined as the set of all vectors x such that the matrix sends them to 0. Okay. Now let's think about the dimension of the null space. Okay. So how can we characterize all the vectors in the null space? How can we better understand them? Well, they are basically the solutions of the homogeneous system, right? And we studied this before, if you recall that. And if you remember, after we reduced A to the reduced row echelon form, then we had, if we had R pivots, then we had n minus R free variables, right? And consequently, n minus R special solutions. Do you remember how we did that? And the special solutions were constructed in a way that they are all linearly independent. Do you remember that? Like if we had like if we said that the free variables are, I don't know, x2, x3, x7 or something, then I said, well, let's pick these values and compute all the remaining ones, all the non-free variables or the pivot variables. Then pick this, compute the remaining ones. Then finally pick this, compute the remaining ones, right? But because I picked parts of the special solutions in this way, they must be immediately linearly independent. It's exactly the same argument as before, right? If I take a linear combination of these three, there could be some x1, there could be a bunch of things here, there could be something. That doesn't matter what's over there, because already these numbers here, they guarantee that they will be linearly independent, right? Because if I put some alpha 1 here, alpha 2 here, alpha 3 here, multiply, like make it a vector, multiply, and I will want it to sum to 0, that this already guarantees that all the alpha 1, alpha 2, and alpha 3 must be 0, just as I said before, the same type of argument. Okay? Okay, so this tells us what is the dimension of the null space. The dimension of the null space is n minus r, because there is exactly n minus r linearly independent solutions to the homogeneous system. So that's an interesting thing to note. The other interesting thing is that that's why the orthogonal complement comes into play, is that notice that the AX can be interpreted in a different way too. One way to interpret it is, as I said here, that's a solution to the homogeneous system. The other way to interpret it is that the X is orthogonal to every row of A. Think about it for a second. So this means, again, you see vector matrix multiplication, right? Looking at every row of A, I'm in the product with X, so that means that they are orthogonal. Every row of A is orthogonal to X. That's exactly what this equation is saying. Everybody sees that? So what that means is that the entire row space of A is orthogonal to the null space. Okay, but what we just shown is that the row space is dimension R, and the null space, as I have just discussed here, has dimension n minus R. So in fact, they are exactly orthogonal complements. So I can write it like this, so that the orthogonal complement of the null space is exactly the row space. This is orthogonal complement. Or I could write it the other way, it will be equivalent, right? The orthogonal complement of the row space is the null space. Okay. There is beautiful symmetry if we look at the left null space. So let's now talk a little bit more about the left null space. It's sort of analogous. Or it's completely analogous, because the left null space from the normal null space only differs by looking at rows instead of columns, or in other words, looking at AT instead of A, right? So the left null space is the set of all vectors y from Rm. Again, remember that our matrix is an m by n matrix, such that ATY is 0, or equivalently YTA is 0. So if I use the same argument as before, if I convert AT to a reduced row echelon form, and if it has rank R, or R pivot variables, then I'll see that there is m minus R special solutions. And again, just like the same argument as before, they are again linearly independent. Okay? So only thing is changed that I have now here m instead of n, because I'm looking at AT. And just like before, what does the ATY equals 0 mean? Well, that means that the y is orthogonal to all of the columns of A. Okay? Because now I have AT here. Normally it would be the rows of AT, but those are columns of A, right? So this says that y, which satisfies ATY is 0, any y from the left null space, is orthogonal to the column space of A, because it's orthogonal to all the columns, therefore the column space. Okay? And just like before, here we see, okay, well, there is no other way. If we have m minus R linearly independent vectors, which form a basis of the left null space, and they are all orthogonal to the column space, which has dimension R, they must be each other's orthogonal complements. So I guess the way, if you wanna write it schematically, so what the matrix, if I have a matrix m by n like this, so what the matrix does, it's a mapping between Rn to Rm, right? The matrix A takes a vector from Rn, maps it to a vector in Rm, right? And what I have just discussed here is that the Rn, the input space, essentially splits into two subspaces: the null space, which has dimension n minus R, and the row space, CAT, which has dimension R. And it maps into Rm. That's the target space, that's the output, that's the results. And in this case, it splits into two subspaces. That would be the left null space, NA transpose, which has dimension m minus R, and the column space, which has dimension R. So notice that everything is cool here, that n minus R plus R is n, and m minus R plus R is m. So these are just like the image, just like the figure before, except that in arbitrary dimension, the subspace basically partitions the vector space into two orthogonal blocks. So that's exactly what happens for absolutely arbitrary rectangular matrix. Of course, it can happen that some of these subspaces can be the trivial subspaces, right? It can easily happen that this R will be 0, so that there is no that there are no non-trivial vectors, or that the null space could be. What I'm trying to say. Or that the R could be n, right? If the matrix has the right shape, so the null space is empty, only contains the trivial, only contains the 0 vector. Or not empty, but trivial. Better term. So I guess let me try to shed some more light on this. Right now you might be confused because it's a lot of terms. Let me do an example to illustrate it with a specific matrix. So let's take a look at some simple matrix and let's see what the subspaces there look like, okay, to give you a little more concrete picture rather than just this ideologic thing, which is fine, but I think it's better visible on an example. So the example I would like to do is a matrix like this, 0, 0, 0, 1, 2, and the last row will be all zeros. So clearly this is a 3 by 5 matrix, right? And I already picked it in a reduced row echelon form, so I don't have to be doing the reduction to reduced row echelon form. That will make our life a little bit easier. It might be a little bit trickier situation in the midterm because I want you to do a little bit more computations, but just to illustrate the subspaces, this is more than sufficient, I think. So first of all, what is the rank of the matrix? The R? 2, yeah, of course. So let's take a look how the subspaces of this matrix look like. So first, let's take a look at the row space. Why not? So that's denoted as CAT, right? And we can directly, it's sort of dumb, right? Because it's already directly written here. So that's the easy one. So like one way I could write it would be alpha times the first row, 1, 3, 5, 7, plus beta times the second row, 0, 0, 0, 1, 2, for any alpha beta reals, right? So notice that the dimension obviously is 2, right? The dimension is the rank, I don't know, it's also usually written just as R, which is 2. So that's an easy one. The column space is also easy. So what is the column space if it's so easy? Because I already chose it in reduced row echelon, that's why it's so easy. If it wasn't in reduced row echelon, then I would have some transformation matrix here, and I have to do a little more computations, but in this case it is easy. So what do you think? How can I write, or like the basis for the column space is particularly trivial, right? So the question you need to ask yourself, what all vectors I can generate by taking linear combinations of the columns of this matrix?
1, 0, 0, 0, 1, 0.
Exactly, yes. So I just I take the pivot columns, right? Easy peasy. 1, 0, 0 plus 0, 1, 0. The other ones will be just a little trickier, not that much trickier. So you already know the dimension must be the same. That's what the theory dictates, right? When indeed it is the case. If it wasn't in reduced row echelon form, if I had some matrix here from the left, then I would have to take the columns on the matrix from the left, because these ones wouldn't cut it. We discussed it the last time. But in this matrix, it's just like this. So let's take a look. The third space would be the null space. So that's our NA. So in this case, I need to think a little bit, because in this case, I need to find the basis of all solutions of this homogeneous system of linear equations, right? So let me do that for you. So here I have, so x1, they would be pivot variables, right? x1 and x4. As opposed to x2, x3, and x5, those would be the free variables, okay? Well, the recipe works like this, that I choose the free variables, and I choose them, it's polite to pick them as a standard basis vectors, and I compute the rest of them, okay? So I substitute, so I'm solving this system of linear equations, where I substituted for x2, x3, and x5, these values. So I start at 1, 0, 0, and I compute the rest of them. So what do I get? From the second equation, I get nothing, right? Because it reduces to, because it already been reduced. And from the first equation, I get, they're all zeros, and I get x1 plus 3 equals 0. So x1 must be minus 3, right? And here x4 there is 0. So oh, that's what I get from the previous equation. Sorry, I forgot. So this was implying that x4 must be 0. Okay, let's do the other one. So the other one, I pick for the free variables, I pick 0, 1, 0. Okay. So let's see, what does it mean for the last equation? That means that, oh, sorry, I did it wrong. That was supposed to be like this, right? x2, x3, and x, let me do it like this, x2, x3, and x5, or maybe like this, x2, x3, and x5 are my free variables, so I am choosing them. So this time I chose them as 0, 1, 0. So that means that the last equation says that x4 is 0, right? So I get again 0 here. And then the first equation says that x1 plus 5 equals 0. So I get minus 5 here. The computations are easy because it's already in reduced row echelon form. And for the final one, I get 0, 0, 1. So the last equation says that x4 plus 2 must be 0, so x4 must be minus 2. And the first equation will say what? So this one annihilates itself, and this is x1 plus 7 must be 0, so here I must put minus 7. Okay? So those are all the special solutions. They form a basis. So that's also the basis of the null space. So the null space can be written like this, as alpha times the first one minus 3, 1, 0, 0, 0 plus beta minus 5, 0, 1, 0, 0 plus gamma times the last one minus 7, 0, 0 minus 2, 1 for any alpha, beta, gamma scalars. Okay? So notice, what is the dimension of the null space? The dimension of the null space is 3, which is exactly 5 minus 2, or if this was n minus r, right? N is 5, rank is 2, so everything is cool. And let's do the left null space. That's gonna be also fairly simple because it's in reduced row echelon. So left null space. Everybody cool with this? Good. So that's NAT. So that means that I have to be looking for the special solutions which satisfy this. So I'm sort of solving now the system from the left. This case, so what it means that I'm looking for 3D vectors y such that if I do these linear combinations, I guess I'm just copying the matrix really, but whatever. 0, 0, 0, 0, 0, and that needs to give me all zeros. Right, so I just sort of rewrote this matrix equation like per component. So what does this mean? This means that the y1 must be 0, right? Because that's what this first column I guess says. Y2 must be 0, and y3 can be anything. Right, because it's multiplied with 0, so it's not going to change anything. So what is the basis of the left null space? Anybody can tell me that? It's going to be 3D vectors. It's going to be a subspace of R3, right? And the first ones have to be zeros, right? For the last one, I can pick whatever. So, for example, 1, whatever non-zero thing, of course. alpha is real. So the dimension of the left null space is 1, which happens to be exactly equal, because that's what it has to happen. That's exactly m minus r, right? M was the number of rows, that's 3, the rank is 2, so indeed everything is cool here. Okay? So I guess if I should put it more specific here in this case, we had an input space which was R5, and was it mapping to R3, right? And we found that the null space, what was it? It has dimension 3. The row space had dimension 2, because that's the rank. So this one also has dimension 2 and dimension 1. So indeed, this all works. So this is just sort of checking that the theory works for one example. It's generally a good idea. Okay, so now I think we are fully prepared for the 4 fundamental subspaces. So here is the thing. Here is the big picture. This is the beautiful diagram. I think it was invented by Gilbert Strang. This is the beautiful diagram which gives you a complete picture what a rectangular matrix does. So I again assume that my matrix is an m by n matrix. So what does it mean? That if I have an R to n space here and R to m space here, that means that my A matrix maps from Rn to Rm, and that its transposition, AT, maps the other way around. It goes from Rm to Rn, right? So basically the matrix is a linear transformation between the two spaces. The transposition is a linear transformation going the other way around. Okay, and here is how we can understand what the matrix essentially does. So the first, the input space Rn, it splits into 2 subspaces which are orthogonal complements of each other. Okay, the first one is the row space. So the row space are all these vectors, all for every y, aty, that's the row space. And its orthogonal complement is the null space. Those are all the vectors which are the solutions of the homogeneous system of linear equations. This one has dimension r, where r is the rank of the matrix. And the null space has the complementary dimension, so n minus r, because these two numbers have to sum to n, because they are orthogonal complements of each other. And they are, it's sort of easy to see that they are perpendicular, because if I take any vector from the row space, which can be characterized as aty, it is orthogonal to any vector from the null space. Why would that be true? Well, I guess it's sort of trivial, right? But let's write it. So xt aty, that's what I have here. You can write as xt aty due to associativity, which is nothing but ax transpose y, but ax is in the null space, so that's 0. So that's 0, right? So indeed, these two subspaces are orthogonal. And because they have the right dimensions, they are exactly orthogonal complements. Okay. So in Rm, in the target space, we have the same picture, except that we are looking at completely different subspaces. We are looking at the column space, and we are looking at the left null space, which are again orthogonal complements of each other by exactly the same argument. In this time, like the ytax equals 0 for all y which are in the null space. I guess I should go a little bit slower. So the column space is formed by all vectors of the form ax, where x is an arbitrary vector from Rn. And if I take an arbitrary vector y from the null space, the left null space, meaning aty is 0, then these two guys will be perpendicular. That's because ytax is 0. Again, I can write the same type of thing. So ytax equals ytax, right? Which is exactly equal to aty tx. But aty is 0, right? So this is 0. So indeed, they are perpendicular. Just like here, it's really like sort of like a mirror type of image of that. The column space has the same dimension as the row space. That's important. Both have the dimension of the rank. And the left null space has different dimension in general, and that's m minus r. Okay, it's because these two again have to add up to the m dimension. Now, how the matrix what the matrix essentially does? If I take an arbitrary vector v somewhere here, so this is an arbitrary vector. So if v is an arbitrary vector from Rn, okay, then the vector can be split into two parts. One part, let's call it Vn in the null space, and Vr in the row space. Okay, so my V split into Vn plus Vr, where the Vn is in the null space, so that means that a Vn is 0, right? And that's because that's basically this. That's this picture just in higher dimension, right? If I take any vector in the space, I can split it in two components, one in the subspace, one in the orthogonal complement of it, okay? So that's what I did to my vector here. So this Vn part that that maps to the origin here, the origin of Rm. So let me draw this origin like this. So this is an origin 0 vector in m dimensions, right? m zeros. Okay. Now this Vr part, it maps by the matrix A somewhere to the column space, not to 0, right? It's also in the column space, to something non-trivial in the column space. Okay. So this basically tells you how the matrix acts on any vector from Rn. It basically splits this into these two parts. This one goes to 0, that's discarded, and the other one actually produces some interesting linear transformation. Now, the A transpose works exactly the other way around, right? I could also take a vector here. It would also decompose into a part in the left null space, into a part in the column space, and again the part in the left null space would get mapped to the origin here, or origin of Rn, and this thing would get mapped to some non-trivial vector in the row space. So this picture is like beautifully symmetric and gives you an entire picture of what the matrix means in terms of linear transformation. Okay. And the most important, I guess, if you want to remember only one thing from this, then remember that in every rectangular matrix m by n, there is basically hiding an r by r invertible square matrix. Because that's what basically this means, right? So because this is sort of like the padding, right? These are the guys that just go to 0. So this is like, can think of it like the fat you can trim. And the only payload is here, if you want to think about it this way. Because the matrix forms a 1-to-1 mapping. So here there will be a 1-to-1 mapping between the non-trivial vectors in the row space, or non-zero vectors in the row space, and non-zero vectors in the column space. See that? All these guys go to 0 here. All these guys go to 0 here. And every non-zero guy here goes to some non-zero guy here, the same way back. It's a beautiful, beautiful picture. So let me summarize the 4 fundamental subspaces here. So this is just a basically a summary of what I described, all these drawings and arrows. So of course the matrix can be interpreted as a function that maps from Rn to Rm, and we have these 4 fundamental subspaces. So the first 2 are subspaces of Rm, the other 2 are subspaces of Rn. I already said it many times, so I don't need to repeat, you just read it. And really the main point is that ultimately you can reduce the matrix to a mapping between 2 r-dimensional subspaces which is invertible, right? If you could isolate the column space and the row space, then you can isolate an r by r invertible component of A, which is not visible there when you just look at the matrix, but it's hiding in there. And these null spaces are basically the ones that get mapped to zeros. Those are sort of like the special cases on the left side and on the right side. Does that make sense? Okay. And I guess what is cool about the 4 fundamental subspaces theorem is that it relies on like fairly elementary mathematics. All we needed to do this were just elementary row operations, right? Just the reduced row echelon form. Basically, a stronger version of this theorem is the SVD theorem, the single value decomposition, which is like the sledgehammer of linear algebra. What the SVD essentially will do, and we will get to it many lectures later, because that requires just a little bit more involved mathematics, eigenvalues and polynomials and determinants and these type of things. What it will give you, SVD, is orthogonal bases for all these subspaces. And the matrix, the R by R invertible matrix that's hiding in there, it will expose it to you as a diagonal matrix. So it doesn't really get simpler than that. So the SVDs were like the big sledgehammer. It pretty much solves almost all problems in linear algebra. The problem is that such a sort of heavy weapon that should be used sparingly, because if you have a million by a million matrix, you probably don't want to be computing its SVD. So I guess sort of give you like a precursor of where we are heading. So ultimately, we'll get to the SVD theorem. But the cool thing about these four fundamental subspaces, it gives you the picture without having to worry about the eigenvalues and SVDs and so on, just with really elementary mathematics. Okay? So that concludes this section, the subspaces. And I guess what we are going to do now is going to start slowly building up towards SVD. Yeah, I think I can just do that. By first discussing orthonormal, orthogonal bases. So that's the next part. That's also what your next project is going to be about, because this stuff has lots of cool applications by itself. So let me start by motivating it a little bit. So again, it's always best to start in R2. So if I ask you to pick a basis in R2, most of you would probably come up with this basis, right? A standard basis. Why complicate things if it's not necessary, right? But if some of you were like a little more creative and picked like a basis like this, right? That would be also a perfectly valid basis, right? If some of you were even more creative and picked a basis like this one would be small, I still could not object, because still a perfectly valid basis, right? Even more creative types could come up with the basis like this. And again, it's a perfectly valid basis, right? The only way you can destroy the property of a basis is if you are so unlucky that you put there a zero vector, or if both of them were on the same line. And that would not be cool, because it would not generate the entire vector, and they wouldn't even be linearly independent. So this one would fail. But it's much easier to work with these bases, with orthogonal bases or orthonormal bases. And that's essentially the point of this chapter. I guess one way to put it, that all bases are created equal, but some are more equal than others. And these more equal ones would be the orthonormal ones. So, basis is, by definition, any set of linearly independent vectors that spans the entire vector space, right? So that's why all these choices here are valid. Not this one, not the one that has zero vector, but all these guys are perfectly fine bases. But if you can, it's usually a great idea to work with orthonormal bases. And orthonormal basis is a basis such that all the vectors are mutually orthogonal. So it means it's still a basis, so it still generates the entire space. But the basis vectors have the property that they have unit length. That's what the normal means. And then the dot product for two different ones is 0. So that means they are mutually orthogonal. By the way, so the orthonormal means that they have length 1, even though the terminology is not completely standardized in literature. I have seen like books like that talk about orthogonal bases, but still assume that they have length 1. The point is that this length doesn't really matter, because it's a very easy matter to just rescale the vectors just to get length 1. It's just divided by the norm, and that's it. What really, the really important thing, the main deal here, is that the dot products between any two different vectors have to be 0, that they are orthogonal. By the way, at this point, I think it's good to know that if you have vectors, non-zero vectors that are orthogonal, it already implies that they form a basis, or I guess I should say that they are linearly independent. That's easier. So if I have non-zero vectors which are all mutually orthogonal, so I just take this part, right? If I take any pair, they will dot product to 0. I guess I should have written it. I said I'll not be using the dot anymore, so ui, t, uj, it's the same notation, or different notation for the same thing. And I'm saying that if any two pairs are mutually orthogonal, that implies that the vectors are linearly independent. Can you think about a proof? The proof is actually very simple. So let's look at it. So let's write it here. So let's assume that I have u1 up to un, such that for each a different from j, the dot product of ui and uj is 0. And I want to say that this implies that u1 to un are linearly independent. So how do I prove this? Well, what do I need to prove? What linear independence means? The linear independence means that if I take a linear combination of the vectors u1 to un, which gives me 0, then that implies that all the alphas must be zeros. That's what linear independence means, right? And proving linear independence means that using this property, I have to prove that this is true. But this is actually very simple, because all I need to do, if I have this, so assume I have a linear combination of the u's, which gives me a 0 vector. Now, please forgive me putting the arrows everywhere. It will be a big mess. All I need to do is dot product this whole equation, with all of them, with all ui's, right? Do you see that? Because if I dot product this with ui, what I will get? I'll get u1 I plus, here will be alpha I somewhere, ui transpose ui, plus up to alpha n, un transpose ui, equals, well, if I dot product 0 with anything, I certainly get 0, right? So I can just write there 0. But look what I assumed. I assumed that they are more mutually orthogonal, right? So these all things, they just fall out. This is 0, so this all is gone. If I, and this ui transpose ui, this must be something non-zero. If I picked, if I had them orthonormal, it would even be 1. But if the vector is non-zero, that's what I said. I didn't really write it there. Let's say there for he, the norm of ui is greater than 0. Then this is a non-zero number, so this implies that alpha I must be 0, right? And I can do this for any I from 1 to n, so I prove that they are linearly independent. Make sense? So that means that the orthogonality is a stronger property than linear independence. If I have a bunch of vectors and non-zero vectors and they are orthogonal, it implies that they will be linearly independent. But it doesn't work the other way around. If I have linearly independent vectors, of course, they don't have to be orthogonal, right? Like these two guys, for example. So indeed, orthogonality or orthonormality is a stronger property, and it's actually very useful. Why is it very useful? Well, first of all, we can define what orthonormal matrices are. So if I have a, mind this, that it's rectangular matrix, where the columns form an orthonormal basis, or just orthonormal set of vectors, I can say that the matrix is orthonormal. So notice that there is a very elegant way to write this, the requirement of orthonormality. I can just write that QTQ is identity. Because again, let me do it graphically. This is my QT, and this is my Q. Yeah, that's correct. I was just thinking about the dimension. These are actually the right dimensions. I will get to that. And this, I want this to be identity. Then what this is saying? This is saying if I take a row of Qt, but row of Qt is just a column of Q, right? And I dot product it with a column of Q with another column of Q, I get the Kronecker delta, right? An element of an identity matrix, right? So this is saying the same thing as I said here, right? This is saying if I dot the dot product, if I dot the vector with itself, I get 1. If I dot it with another 1, I get 0. So indeed, this is basically an elegant way of saying that all the columns of Q are orthonormal. QTQ equals IN is a matrix way of saying that the columns of Q are orthonormal. Everybody sees that? Great. So if I was lucky and M equals N, if I have a square matrix, then the inversion of the matrix is, and it's an orthonormal matrix, then it's just transposition. I think we were talking about this before, right? We need to talk about square matrices because not square matrices are we haven't defined inversion for non-squared matrices. But for square orthonormal matrices, their inversion is just transposition. And that means that like solving systems of linear equations gets really trivial, right? So if I have a system Qx equals b, then the solution, well, I know I don't have to be computing anything. I just transpose the matrix, which is just like that simple operation, and I get the solution immediately. By the way, let's see. Yeah, I think that makes sense to make this note here. I think I mentioned it before, but it's important, so I'll mention it again. So, because you know that if I have the square, let's talk about the square ones. Square orthonormal matrices. So Qt is the Q inverse, right? But from group theory, we remember that this is the same as QQ inverse because there is no difference between left and right inverse, and the invertible matrices form a group, so that must be the case. So this is also equal to this, right? QQT. Right? What means QQT? QQT is something, or what means QQT equals identity? Just like I interpreted here what QTQ equals identity means, it means that all the columns are orthonormal vectors. What means QQT is identity? Exactly, all the rows are orthonormal vectors, right? So that means that if I have a square orthonormal matrix, then it doesn't matter if I talk about the rows or columns because both of them are equally orthonormal. Or in other words, if I have a square orthonormal matrix, then the fact that it has orthonormal rows implies it has orthonormal columns and the other way around. Oh, by the way, as I was sort of debating about these dimensions, because if you can get it, if I got it wrong, it actually would not work. So let's see. So if my Q was like this, can it be an orthonormal matrix? Can all the columns be orthonormal vectors? If I have a matrix of this shape, the short and fat matrix, if this was my Q, could it possibly be an orthonormal matrix according to this definition? Could all the columns of this matrix form an orthonormal basis? They can't, right? Why? Can you give me a quick argument? That's right. Because this is M and this is N, right? So I cannot have N plus 1. I cannot have even M plus 1 linearly independent m-dimensional vectors, right? That's what we know, and we know that orthonormal vectors are linearly independent. So if we put it together, this would be impossible, right? So yeah, I can have at most the dimension of the space orthonormal vectors. So that's why I sort of hesitated by drawing the dimensions. Okay, so here is one more property. of orthonormal matrices that they preserve the norm, in the sense that if I take a vector y and I transform it by an orthonormal matrix, in this case it doesn't even have to be square, it can be rectangular, or I can write it equivalently in the other way around. Then the norm of the resulting of the transform vector is the same as the norm of the vector I started with. That's very easy to see, right? Because the norm is just x dx. But if x is qy, I can write it like this, because this is whole transpose. This is ytq tq. But q tq is identity, so clearly the norms are the same. The same way, I could also say that the dot product is not changed, right? That x dy, if I transform both of these guys by q, so if I do qx transpose qy, exactly the same argument gives me that xtq tqy is xty. It's sort of what I started. I guess I don't really have to write this. The point is that these two are the same, because this is okay. I guess I should have written it. Again, at this point of the lecture where I'm starting to make a lot of mistakes because it's already been a long day. That's what I wanted to write, that if I transform both of the vectors by q, then the dot product doesn't change. Consequently, the angle between two vectors doesn't change. If you think about it logically, it makes sense, because if I have some two vectors with some angle in between, and I apply a rotation, that's what orthonormal matrices are, then the angle doesn't change. We have almost gotten to transform coding. There is one beautiful application of orthonormal matrices. It's so beautiful that I think it's going to be your next project because it has uses in data compression. And I think I will need to spend a little bit more time explaining this properly. But the point is, I can give you the spoiler at least, or overhang, if you will. The point is that if I have an orthonormal basis, I can think of it as a rotation, as a change of coordinates, right? Remember what we started with, change of coordinates, expressing things with respect to different bases. But here, the dimension of the space can be gigantic. Like your image with million pixels, that can be your vector, and this could be a matrix million by million. And if I have an efficiently computable orthonormal matrix, I can use it to create new coordinates for an image. And if I pick the Q wisely, like the discrete cosine transformation, then the coordinates will be much more sparse, in a sense, than the original system, than the original vector, and I can use it for a beautiful lossy compression mechanism. That's what's used in JPEG and all that. And I will give you more details on that on Wednesday, and I think this is also going to be our next project, to try the discrete cosine transformation. So there is more to it. I need to go over this properly, and I will do it the next time. It's really cool, and the orthogonal matrices, that's the basic of it. Okay, all right, already packing up. Any questions? Okay, you can go.